Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Kirill Chemrov. Kirill received the bachelor degree in applied mathematics and physics from Moscow Institute of Physics and Technology this year, and he is currently pursuing master degree. He joined the Institute for Information Transmission Problems in 2020. He is currently a junior researcher at the wireless network of IITP RAS, and his research interests include real-time applications support in Wi-Fi networks. Today he will present us new methods for serving RTA traffic in Wi-Fi networks. Kirill, the floor is yours.
Thank you, Vyacheslav, for introduction. Now I'm ready to start and want to make a brief introduction. The popularity of cloud gaming, virtual and augmented reality, industrial automation, video streaming, and other real-time applications, or shortly RTA, is rapidly growing. And the problem is that these applications impose strict requirements on delay and reliability. We also can talk about real-time traffic as time-sensitive traffic, and originally for Ethernet networks, time-sensitive networking or TSN substandards were created to ensure zero packet loss due to buffer congestion, extremely low packet loss due to equipment failure, and just guarantee upper bound of end-to-end latency. And now this TSN framework is making its way to wireless networks. But sure, there are much more difficulties in wireless communication apart from buffer congestion or equipment failure. But still, it's a common problem in wireless networks. For example, in cellular systems, this problem is known as providing ultra-reliable low-latency communications, or URLC, which is perhaps the most revolutionary part of 5G systems. But what do we have for Wi-Fi networks? And actually, it's a good question, because serving RTA traffic is challenging for Wi-Fi because of unlicensed spectrum and working with random access based on carrier sense multiple access with collision avoidance. That means that during a long transmission, none of the stations in the neighborhood can interrupt it and access the channel. What is more, collisions between frames from different stations can also degrade transmission reliability. Nevertheless, to address this problem in Wi-Fi networks, the IEEE 802.11 working group has created an RTA TIC, topic interest group, and this group has classified RTA scenarios and defined quality of service or cost requirements for such traffic. And as a result, despite the difficulties described above, the support of RTA has become one of the targets for future 802.11be amendment to the Wi-Fi standards, also known as Wi-Fi 7. Moreover, ultra-high reliability is a new study group within 802.11 working group that will investigate PHY and MAC technologies to improve reliability of VLAN connectivity, reduce latencies, increase manageability, and so on. Sure, as any study group, the aim is to create a task group next year, which will work on amendment for future standard. Well, now I want to outline my speech. As you can see, we have already gone through introduction, and then I'm going to describe in a few words the scenario and the general RTA traffic service problem, some KPIs, and so on. And then I'd like to discuss briefly existing mechanisms that can be used to support RTA in Wi-Fi. And then I will introduce some RTA support methods that then will be compared with help of numerical results. Yeah, and surely, finally, I will conclude my speech. Let me move on to the scenario. We consider heterogeneous Wi-Fi network. It means that apart from access points and RTA stations, there are some non-RTA legacy stations that probably do not support the latest amendment to the standard. And here I want to emphasize that we consider only uplink traffic, and all the stations generate some kind of uplink traffic. I don't want to specify which kind of traffic. I will talk about it later before numerical results I'm analyzing. Now I want to know that we consider the following KPIs, or just coarse metric for RTA stations and non-RTA stations. For RTA station is Q quantile of delay. It means that it's a delay which can be guaranteed with probability Q. And here I want also know that we consider the perfect channel condition and that every station can hear each other. There are no hidden stations, and packets can be lost only because of collisions. That's why the reliability can be described by the probability with which the delay bound can be guaranteed. So here is Q is kind of it corresponds to reliability, and the general quantile is correspond to delay. As for non-RTA stations, we also want to consider some kind of cost metric for them. Sure, it will be easy to just watch it throughput, but with ideal channel condition, we can choose any bit rate, and I think it's not really realistic to look at throughput. That's why we consider channel usage efficiency, and by this term we consider the portion of time when non-RTA station successfully transmits its payload. And sure, if you want to find throughput, you can just multiply efficiency and choose a bit rate. Yeah, but now we're talking about efficiency. Still, there is a question what kind of delay we want to consider, and probably we can call it MAC delay, medium access control delay, because between two MAC layers on the receiver and the transmitter. But more precisely, I want to define it as follows. The RTA transmission delay is the time between data frame generation and ARC reception on the transmitter or by the transmitter. And in order to just for more understanding, I want to decompose the delay in three main parts. Firstly, when the RTA frame is generated, the channel may be busy, and the station have to wait till the end of the transmission, and when the channel become idle. Yeah, it's the first part. We can denote it as a waiting delay or waiting for the busy channel delay. Then, after the channel become idle, it starts back-off countdown, and during this back-off countdown, other station can transmit their frame, can be involved in collision, and even RTA station under consideration can also be involved in collision, and hence then try to retransmit, and all this time we will denote it as contention delay. Yeah, and finally, sure, there's a small part of delay which corresponds to the transmission of the data frame, but I want to know that we consider the transmission delay includes transmission of the data frame and then receiving the acknowledgement. Well, and now I want to talk about existing approaches, how we can reduce this delay. A good idea to reduce contention delay is using some kind of scheduling, and fortunately Wi-Fi standard provides us such an opportunity. For example, 802.11ax introduce orthogonal frequency division multiple access, or WaveDMA. In general, WaveDMA allows the AP to allocate different subcarriers of the same channel to multiple stations. for simultaneous reception or transmission. But in particular, as we are talking more about uplink traffic, let us consider an uplink OFDMA transmission. This transmission are controlled by the AP, and it starts with a trigger frame that's broadcastly transmitted by AP, and then it contains some information about resource units allocation. Resource units is just a time frequency block, which can be allocated for a particular station. And then after all station transmission, that should last the same time, the AP transmit multi-station block ACK. Here the main part is that AP has an opportunity to allocate resource units either for deterministic access or for random access. As for first one, AP can allocate just one RU for a particular station, and sure, it's kind of scale access, so there's no collisions, so on. But the problem is that AP has to know which station and at what time want to transmit, when it has some frame to transmit. At this point, transmission of buffer status report by station causes additional delays. The situation is different for random access, which is also called uplink OFDMA random access, or WARA. With such random access, station transmits data according actually to access mode, which is similar to Aloha, and it has low efficiency for a large number of stations. But still, it's worth noting that that some papers also suggest improved versions of WARA and deterministic access, probably some combinations and algorithms. For example, it's a good idea just to allocate for deterministic access one RU for deterministic access for several stations in case of low intensity of RTA traffic, or also it can be feasible. It's feasible just to copy one frame and transmit it in different RUs in one OFDMA transmission, just in order to enhance reliability. There's also another mechanism that can be used to schedule the channel access, which is called restricted target wake time. Initially, target wake time is a mechanism that enables scheduling of data exchange between AP and a station, which on one hand minimizes the medium contention, and also allows, first of all, I think allows power saving stations to reduce power consumption by explicitly identifying the time periods when they should be awake to transmit or receive data. And also Wi-Fi 7 extends TWT by introducing a mode called restricted TWT that defines enhanced medium access protection and resource reservation mechanism for an AP to provide more predictable delay for delay-sensitive traffic. The broadcast TWT mechanism is extended to allow an AP to announce the scheduling of RTWT service periods, and any non-AP station that supports this feature can sign up to become a member of RTWT retransmission and RTWT procedure probably. And also for further medium protection, any non-AP station that supports RTWT is required to end its take-stop before their service period. And sure, if there is not enough time and there is no opportunity to reduce the take-stop, the station shall defer the transmission. But still, there is a problem that RTWT is an optional mechanism, and such service periods can be ignored even by new Wi-Fi 7 stations. Sure, there is an opportunity for an AP to announce quiet intervals during which any other non-AP stations that are not member of RTAA, just in order to prohibit their access to the medium. And there is an opportunity, at most one quiet interval, to overlap with RTAA, and it's called overlapping quiet interval. But Wi-Fi 7 stations that don't want to support RTAA can ignore even such overlapped quiet intervals, and actually it's make this mechanism unreliable in general. Now let me move on to the probably key novelty of Wi-Fi 7. It is a multi-link operation. In general, it provides an opportunity for one device, one Wi-Fi device, to transmit and receive via several links. For this, the standard introduced the concept of multi-link device, or MLD, which can be considered as several affiliated stations with common interface between the medium access control and logically control sublayers. Well, if the spectral distance between links is large and the antennas are rather far from each other, the cross-channel interference is small enough. So the station, well, probably it's better to call it MLD. The MLD can access the channel via several links. It just can MLO allows an MLD, a client MLD associated to an AP MLD, to establish several links between each other for data transmission. And by default, all the frames can be transmitted with all available links. However, 11BE defines a TID link mapping mechanism that allows mapping only specific TID to some links and forbid frames of other TIDs to transmit via these links. TID stands for traffic identifier, and for example, we can take a TID related to the RTA traffic and map it to some particular link, and forbid other stations to transmit via this link. As a result, we kind of isolate RTA traffic in one link, and sure, in such a way we can avoid contention delay and even waiting for non-RTA transmission delay. But the problem is here that in presence of legacy stations from alien BSSs, the problem is that this station can use the link that was mapped for RTA TID, and as a result, it ruins such isolation. What is more, TID link mapping is optional, and even on new Wi-Fi 7 stations can ignore TID to link mapping negotiation and just use the default mode when all frames can be transmitted via all links. And it also disrupts the reliability of RTA transmissions. But fortunately, there is it's not the only way how to use MLO for RTA support. For example, RTA station can just try to access the channel in different links and transmit urgent data in the first available one. We also can go further and just copy RTA frames, called RTA duplication, and when the data frame is generated, station can make a copy and try to transmit all the copies through all available links. And as a result, it increases channel access delay because the resulting delay is a minimal delay among all the links. What is more, this approach enhances reliability, even in presence of interference and bad channel conditions. But I think I just want to emphasize that there is one problem, that such an approach increases the congestion just because of transmitting a lot of copies of the same frame. It's not that I think I want to know that some methods were developed and investigated even before MLO became a part of Wi-Fi standards. For example, one of interface can be used to maintain control channel. in which RTA station can transmit some kind of busy tone when RTA data is generated. As a result, if all the stations in the network is listening the control channel, they should interrupt their transmission when they listen to busy tone, when they detect it, and as a result, we can decrease the channel access delay just because of decreasing the waiting time of non-RTA transmission. But still, this approach is unreliable if there are some legacy stations that do not support such control channel. Sure, there are some other MLO approaches to support RTA, but in general, I want to emphasize that the main problem is that MLO require for RTA device to have more complicated PHY, for example, just additional interfaces, and it makes such devices more expensive. That's why I also want to mention some easy way, and some simple approaches to support RTA. Some of them based on UDCA enhancements. For example, some papers suggest to create a new access category for RTA traffic, or even several ESCs, just in order to make the highest priority for RTA traffic, up to just excluding the contention between RTA traffic and RTA frames and other frames. Also, some papers introduce preliminary back-off countdown. It means actually this approach is used. It can be used if the RTA traffic is predictable, and if RTA station expected some frame generation, it can start countdown its back-off earlier. And yeah, another example is scaling the traffic to reduce inter-IC contention. It's more about reducing delay corresponding to contention of the frames from the same station. For example, there is not to enqueue frames that correspond to non-RTA traffic before RTA traffic, RTA frames are served. Yeah, just an idea, not to put non-RTA frames in a queue before RTA1. Well, I think I'm done with existing approaches, and now I want to describe investigated RTA support methods. Yeah, the idea is to support RTA even in heterogeneous network, and not to complicate the PHY, for example. Let me remind you the delay components, and let us think how we can reduce them. For example, the simplest part is transmission delay. To reduce it, we can just decrease the RTA rate of frame duration, and unfortunately, it also decreases the contention time a bit, because the contention between RTA stations will be decreased because of reducing collisions and reducing the waiting for transmission of winning RTA stations. And in this case, the biggest impact on delay is contention between RTA and non-RTA stations. And in order to reduce it, or probably avoid it, we suggest to set EDCA parameters to guarantee that RTA station always win the contention with non-RTA ones. And to do it, we have to hold this condition. Here, W-min and W-max correspond to minimal maximum value of contention window. Yeah, and the idea is to set them less than the difference between IFSN for non-RTA and RTA traffic. Yeah, here's a illustration just to explain this simple idea. If this condition holds, after busy channel, the RTA station will wait its IIFs and then start the off countdown, and we guarantee that the station will end the off countdown before non-RTA stations just waiting, finish waiting its IIFs. Yeah, just because IIFs for non-RTA stations is much longer. And as a result, the main part of delay is waiting for the busy channel. And there are some methods how to reduce it. First of all, it's tuned TDCA. We called it tuned TDCA, but still it's just, we just continue to set TDCA parameters. And yeah, obviously we can just reduce the TXOP limit for non-RTA stations. Yeah, I can remind you that TXOP limit defines the maximum time a station can occupy the channel. Yeah, sure, the idea is clear, I think. If we reduce TXOP limit, the busy channel time, the maximum busy channel time will be also shorter, and that reduces the general delay. But on the other hand, it also decreases the efficiency for non-RTA stations, because the portion of payload in one non-RTA transmission will be less than with bigger TXOP limit. Yeah, that's why we decrease efficiency. And it motivates us to consider some other methods. And here we introduce preliminary channel access. This approach can be applied for predictable RTA traffic, but actually we demand from the predictability of traffic just that RTA station you have to expect data arriving in some T expected interval. Yeah, if it expects data arriving in this interval, it can begin channel access TPCA before the start of this interval. And it starts it with generating RTS frame, just to perform traditional RTS-CTS procedure. And the idea is as follows. If the RTS frame will, if RTS frame is transmitted in time before data arriving, the channel will be reserved. Actually, the channel will be virtually busy for all the stations except for the stations that perform PCA procedure. And as a result, when the data frame is generated, he transmits without any contention or waiting delay. But sure, otherwise, if data frame is generated before RTA transmission, the RTA station just discard RTS and perform traditional channel access only with data frame. Here I want to mention that we choose TPCA as such value. It includes the maximum busy channel time, TXOP limit, yeah, it's IIFs time, and back-off countdown if all the slots are empty, and the RTS-CTS transmission time. But sure, there is a problem that if there are a lot of RTA stations in the network, PCA leads to significant delays because of waiting for another RTA station's PCA procedure, because they cannot transmit during this reservation. And this fact motivates us to consider an improvement to this method. We call it smart preliminary channel access, or smart PCA. Here's some condition. I probably described it a bit later, but yeah, just some condition. And if it holds, the station use just simple channel access with PCA that was described above. But otherwise, there is a improved channel access method, and the idea is as follows. After RTS procedure, the RTS station should transmit SPCA frame. Yeah, it's just a special frame that we called SPCA, and it should contain information about the expected interval. For example, its duration and time when it begins. And also this frame allows other RTA stations with data to transmit during this reservation, but only if their transmission ends before the expected interval. Yeah, as a result, if RTA station receive such as a PCA frame, it can transmit or even content with other station and retransmit, but before any transmission, RTA station should ensure that its take stop will end before the expected interval. Here I want to emphasize that we have to choose T-Smart PCA a bit longer than TPCA because of transmission of Smart PCA frame. And yeah, the difference from PCA is as follows. The other RTA stations can transmit during another RTA station reservation. Yeah, and sure, it will improve delays, and we will show it from numerical results. But now I want to go back to the condition and explain it. The first one is no more than one RTA station. Yeah, sure, if there are only one station in the network, there is no sense to transmit as PCA because no other station can transmit during your channel reservation. And the second condition is about such fact. Yeah, if it's holds, there is no chance for any RTA stations in the network to transmit during another reservation interval. Yeah, the idea is that if this condition holds, these reservations are always too short to transmit a packet from some RTA station. Well, I think I'm done with the description of these methods, and I'm ready to analyze some numerical results. But first, I want to remind the scenario and clarify some details. Yeah, we consider a heterogeneous network with AP, RTA stations, non-RTA stations, and the channel conditions are perfect. Every station here are there perfectly, and there are no hidden stations. And the packets can be lost only because of collisions, because there are no noise. And as for non-RTA stations, we consider that they support 802.11n standard. We fixed the number of them. Yeah, there are only 8 stations. All the transmissions last the maximum available length. It's defined by take stop limit, and actually the traffic from non-RTA stations is saturated. They always have frame to transmit. As for RTA stations, we consider that they support the latest amendment to the standards. The number of them will be denoted as M, and the transmissions last for all the stations and in all the cases half a millisecond. And also the traffic is some kind of quasi-periodic. The idea is as follows. The expected time has a period of T period, expected time of frame arrival, but the real time is normally distributed around the expected one with a standard deviation sigma. And also cycles of different RTA stations are shifted relatively to each other by a random value distributed uniformly in interval of 1 period. And as for the expected interval, we define it as 10 sigma around expected frame arrival time, just because it guarantees the high probability of frame arriving in this interval. Well, I think I'm ready to move on to some plots. And firstly, I want to discuss impact of the RTA stations number. Yeah, and I want to remind you that we consider 2 cost metrics, one for RTA stations, it's quantile of delay, and efficiency for non-RTA stations. Efficiency stands for portion of time when non-RTA stations successfully transmit its payload, their payload. And here are two plots. The left one is quantile of delay against number of RTA stations, and the right one is about efficiency versus number of RTA stations. Also, you can see here, apart from 3 methods under consideration, I mean, 2DCA, PCA, and Smart PCA, 2 other methods. The first one is default EDCA. It stands for just traditional channel access with EDCA, where RTA traffic corresponds to a voice access category, and non-RTA traffic corresponds to best efforts. As a result, you can see that the delay quantile is pretty big. It's more than 20 milliseconds, and it's incompatible with RTA service. As for multilink, this method is about multilink operation with frame duplication, and we consider 2 links. Here I just want to emphasize 2 facts. Firstly, yeah, sure, it's improved delays, almost halves the delay in comparison with the default EDCA, but still method under consideration provides better delay, and that's why probably there is no reason to compare it with multilink. But the main reason not to compare multilink with other methods is that they do not exclude the combining with multilink operation, and probably just research on a different combination of multilink and these approaches can be a topic of our future work. And now I want to compare just 2 EDCA, PCA, and Smart PCA methods. Here we can see that, yeah, for example, one RTA stations in the network, Smart PCA and PCA show the same results because the procedure is the same, because the condition in Smart PCA methods are hold, and yeah, the procedure, channel access procedure in Smart PCA and PCA similar. But with increased number of RTA stations, PCA method shows worse delay, and sure it can be, and I think it's notable that it shows delays even worse than 2 EDCA, and it can be explained by the fact that PCA procedure consume a lot of channel resources, and moreover, other RTA stations have to wait until the end of another RTA station PCA procedure, the reservation, and hence increased delays. But also, I want to emphasize that it's hard to compare by these plots all of these methods, because on the one hand, Smart PCA provide the best delay quantile, but on the other hand, the efficiency is worse than in 2 EDCA, and in order to provide better delays with 2 EDCA methods, we have to reduce the XOP limit significantly, and as a result, the efficiency will be also reduced. And that's why I want to show you the impact of the XOP limit value. Again, yeah, here we can see quantile of delay and efficiency against the XOP limit. And let me start with quantile of delay. As you can see, 2 EDCA and PCA plots as a monotonic behavior. They just increase with the quantile of delay increase with XOP limit value, and it's obviously because with long non-RTA transmissions, the delay will be increased because of increased waiting for such transmissions. But as for Smart PCA, we can observe that from some value of the XOP limit, it reaches constant value, and it can be explained. Actually, it's hard to explain the behavior of quantile of delay because it's pretty unpredictable, rather unpredictable, I think. But here is the idea is simple. If the XOP limit is pretty small, there is no chance for other RTA stations to transmit during another RTA station observation, and hence with the increased value of TIC-SOP limit, the delay will also increase. But from some value, with some value, TIC-SOP limit value, the time of channel reservation becomes pretty long, rather long, and there is the probability of other stations to transmit during this reservation is high enough, and actually the delay quantile just do not depend on TIC-SOP limit value. Let me move on to the efficiency plot. Here we also can observe that DCA just is a monotonic increase with increased TIC-SOP limit, and it can be explained that by the fact that with increased value of TIC-SOP limit, the portion of payload in one transmission also increased, and hence we improve efficiency. But as for PCA and smart PCA, we can observe some kind of peak on the plot and non-monotonic behavior, and it can be explained by the trade-off between two facts. First one, the same as for 2T DCA, but on the other hand, with increased value of TIC-SOP limit, the PCA procedure also increased because TPCA time depends on TIC-SOP limit, and as a result, on the one hand, with the increased TIC-SOP limit, the efficiency is growing, and on the other hand, it's can be decreased, and here we obtain some kind of peak. And I think it's also difficult to compare methods by these two plots, and I suggest to make some kind of parametric plots with TIC-SOP limit as a parameter. It looks like this. Here we have efficiency versus delay quantile, and every point corresponds to specific value of TIC-SOP limit. Yeah, and even horizontal part of PCA and smart PCA plots correspond to the fact that there is no sense to increase, for example, the TIC-SOP limit because of such monotonic behavior, and we just stop the maximal point. So here we consider 3 RTA stations in the network in period of 20 milliseconds with sigma 10 microseconds. And well, if we observe the right part of the figure where the RTA requirements are not really strict, I mean the delay quantile more than 5 milliseconds, the best method is 2T DCA because it's easier and just provide better efficiency. But if we look at the strict requirements, less than 4 milliseconds of quantile delay, we have to decrease significantly the TIC-SOP limit in 2T DCA method. But on the other hand, for smart PCA and PCA methods, there is no need to reduce it, and hence this method provides better efficiency, and as a result we can get a gain of 100%, for example. We also can compare PCA and smart PCA methods, but actually, according to condition in smart PCA method, we use it only if it's better than PCA. That's why the area of smart PCA application, the area of efficiency and quantile requirements is bigger for smart PCA. And I also want to just talk about another example with lower intensity of RTA traffic with a period of 50 milliseconds and the same sigma. As you can see, with lower delay, the area where smart PCA method is better than all the other is bigger, and it can be explained by the fact that with for lower delay, the impact of PCA procedure consumption, consumption of channel time by PCA procedure is lower, just because the intensity of RTA traffic is lower, and hence this approach can provide improved efficiency, for example, in comparison with tuned UDCA. And finally, I also want to, I want to mention the dependency on sigma. Yeah, here are two plots, the same plots, efficiency versus delay quantile. But here we have 5 RTA stations in the network and period of 100 milliseconds. But on the left one, the sigma is 10 microseconds, and the right one is bigger. It's 100 microseconds. And the idea is that here we also observe a pretty big area where smart PCA provides some gain. But as for more unpredictable traffic, yeah, as biggest sigma provides us with more unpredictable traffic. And as we can see, the area where smart PCA shows some gain is just become negligible, and also the gain is also negligible, and it can be explained by the fact that T expected interval, which is equals 10 sigma, becomes too big, and the problem of this interval is that no other station can transmit during this interval. As a result, on the one hand, RTA stations have to wait till the end of such intervals, and the delay is increased. And on the other hand, it's not profitable for non-RTA stations as well, because the expected interval is just a channel time consumption when non-RTA stations would like to transmit. Well, actually, I think I'm done with numerical results, and I want to conclude all my speech and just to emphasize probably main points. Yeah, first of all, serving RTA traffic is challenging for Wi-Fi networks, but still RTA supports a target for future Wi-Fi networks, and there are some mechanisms to support it, but the problem is that presence of legacy stations disrupts most of the new mechanisms. And to improve the situation, we propose smart preliminary channel access for serving predictability traffic in such heterogeneous Wi-Fi networks with legacy stations and new stations. And actually, these methods can provide significantly lower delay than just simple preliminary channel access in presence of multiple RTA stations. And also, if the delay requirements are strict enough, just probably maximum delays less than 3 or 5 milliseconds, and the intensity of RTA traffic is low, this method is the most effective. And also, I want to note again that this approach, smart PCA, does not exclude the use of multi-link mechanism, and probably it's not obvious how to combine them, and it's this combination can be studied in future. Well, actually, thank you for your attention, and now I'm ready to answer your question, if there are any.
Thank you, Kirill, for your talk. We have at least one question in the chat window.
Yeah, I see. I can read it. I think it's correspond to this slide. In the experiments, YT period equals 100 milliseconds, while delay budget is 10 milliseconds. Typically, the period should be approximately equal delay budget. Well, frankly speaking, here is an example more about the dependency from Sigma. I mean, just to show that smart PCA is should be applied in case of predictable traffic. And I don't think that these scenarios should be realistic. The idea is just to show that smart PCA is about predictability of traffic. Yeah, of the same order. Probably the first examples where we have quantile of delay up to 10 milliseconds and a period of 20 milliseconds. It's, yeah, I think it's more realistic because T period and Sigma, not Sigma, but delay budget are of the same order.
Can you clarify, please, the proposed mechanism you presented, preliminary channel access, and as I understood, the idea of PCA is to reserve the channel in advance before the arrival of RTA traffic. Could you please clarify when the station decides to reserve the channel and so?
Yeah. Okay. Yeah, as I said, RTA station expects data arriving in some interval. We call it the expected interval. And we also propose a time TPCA. And well, when it's such time when before this T expected interval, the time equals TPCA, the RTA station starts the PCA procedure. I mean, generate RTS and try to transmit it. So the idea is that there is some time expected when RTA station expects the data, and the RTA station have to start channel access in advance by the time equals TPCA. Yeah.
Okay, but maybe you have already studied that some methods, for example, to reduce TPCA interval to increase to decrease the channel consumption by RTA stations, or it's something like future work?
Yeah, actually, it's a good question because it's a good idea just to state an optimization problem to find an optimal value of TPCA, just in order to provide, for example, some delay bound and get the best efficiency. Now we just choose it somehow with a heuristic approach because we choose the most probable situation when RTA station, only one RTA station generates, not generate, just wait RTA data while the channel is busy, and the worst situation if it start waiting the data in the beginning of the busy channel and the length of busy channel is takes off limit, then it should wait IFs, backoff countdown, and so on. Yeah, and experiments show that if we decrease a bit this value, it will the delay quantile will suffer significantly, and if we decrease it a little bit, sure the efficiency will significantly worse, but there is no significant impact on delay. That's why it's some kind of quasi-optimum value of TPCA. Yeah, and also we choose T-Smart PCA a bit longer just because of transmission of additional frame.
Okay, thank you. And I have also one more question about tuned EDCA channel access method. which parameters of DCA use is used for traffic in your experiments?
Yeah.
Because the parameters of tuned DCA method depend on them, so maybe I missed them.
Yeah, actually, I didn't mention it, just not to dive in details, but I think it's necessary parts. And in this experiment, we propose to choose IFSAN for RTA station for RTA AC equals 2, IFSAN for non-RTA stations equals 10. As a result, the difference is 8. So we choose W mean and W max equals each other and equals 8. Yeah. As a result, we have an equation here, not an equation. Yeah. Yeah. This means that IFSAN for non-RTA minus IFSAN for RTA equals 8, and the contention window is also equals 8. And actually, that's why we consider not a lot of RTA stations, just in order to not to raise the congestion of frames because of retransmission. I mean that 8 contention window equals 8 is enough for 3 or 5 RTA stations.
Okay, I guess that means that this tuned DCA method can be used only when we have only a single access point is operating in the area, because if there will be at least 2 access points, the proposed scheme will be broken, because the default values of IFSAN are much lower.
Yeah, actually you're right. Probably that's why premium channel access can improve the situation, because other BSSs will listen to RTS, CTS, and maintain the channel as virtually busy.
Yeah, I agree. So we have one more question in the chat window.
Yeah, I can. During SPCA reserve time, how is the contention between RTA stations organized? Do the RTA stations perform the back-off procedure, but the non-RTA stations keep the back-off counters frozen? Yeah, actually, you're absolutely right. The idea is that the channel is virtually busy for non-RTA stations, and the channel access procedure for RTA station remains the same. Yeah, they just contend, they just use the same contention windows. Probably this thing also can be improved. For example, change the contention window sizes and so on. But in this experiment, we do not touch it. Yeah, the main difference of channel access in the reserved interval and out of it is that in the reserved interval, RTA stations have to ensure that their transmission ends before the expected interval.
I have one more question. My question about the parameters of the simulation and the on this slide you show that the traffic is generated with period T sub period, and what about the traffic generation of different stations? Are the T period are shifted, or they coincide, or how?
Yeah, yeah. There is some information on the slide here that cycles of different RTA stations shifted relative to each other by some random value uniformly distributed in one period. Yeah, and sure, it's also some random value of this shift. But yeah, they do not coincide. just shifted relatively to each other. Number here, probably there is another periods for, I mean for another station, and probably they can just have the same T expected, not T expected, but the same expected frame arrival time. Yeah, because it's just a random value and it depends on the simulation.
Have you studied maybe some scenarios where the cycles are not distributed uniformly, but somehow correlated? For example, when they have the same shift, or in one case, and maybe in some other case that they are going just one by one, and you have no contention between RTA stations. Have you considered such scenarios in your research?
Well, actually, during conduction of the research, we consider a bit such situation, but they are not really interesting, because if there is a zero shift, so that every station generates data at the same time, there is a congestion of frame, and the contention between RTA stations really harmful for delays. And when the shift is fixed and the probability of contention between RTA stations is too low, then there is actually no reason to try to allow, for example, them to transmit during another RTA reservation. I mean, there is no need for smart PCA. But on the other hand, the problem is that it's hard to imagine a scenario when it's easy to control the periods of the stations. Probably we can also consider that there are different BSSs with some real-time traffic, and it's also hard to coordinate different APs. Probably it's more about future Wi-Fi networks with multi-AP and so on, just to control the traffic of different stations.
Okay, thank you.
Yeah, thank you for your question.
So I guess that's all for today. I want to thank Kirill for his interesting presentation. I also want to thank guys in the chat for interesting questions. So thank you all for participating in Moscow Telecommunication Seminar. See you. Goodbye.
Yeah, thank you. I'm glad to participate too.